Hi. Hi, everyone. Welcome to the third plenary session of the day. I'm Suzanne Gildert, and I'll be chairing the session today. We have three amazing speakers lined up for this session. Each speaker will have 30 minutes to present, and then, if time permits, we'll have 10 minutes for Q&A after each talk. One small announcement before I introduce our first speaker. We have found a lost Visa card from the Bank of China. So if anyone has lost a Visa card, please check in at this desk over here to my left with your name, and we have your card. Okay, so little announcements out of the way. We are going to start with our first speaker. And really, this speaker requires no introduction. As a physicist myself, Sir Roger Penrose has been and continues to be one of my greatest inspirations. And I know from talking to people over the last 2 days that he's inspired many people here too. He's currently the Emeritus Rose Ball Fellow at Oxford, and his 2020 Nobel Prize in Physics was bestowed for showing that black holes are robust predictions of Einstein's theory of general relativity. He also proposed a solution to the measurement problem in quantum mechanics, objective reduction, which he suggests is also the origin of consciousness, leading to the OR theory. Together with Stuart Hameroff, that forms one of the major focuses of this conference. So welcome, Sir Roger.
Hello. Shall I start? Hello?
Yes, Roger.
Okay. I thought I would start by a short anecdote which came about just the other day. I've been communicating with Andrea Morris, who is a journalist in Toronto, and I had said to her that I had two papers that I needed somehow to bring together and extract the common feature of both of them, and that I was going to get a student to do it. So she said, oh, well, why don't you get AI to do it? So I thought, well, look, it's not going to be much help, but why don't I try it for a joke or something like that? So she then, just the other day, sent me what the AI system had done. As I expected, it was complete gobbledygook, and I gave it 0% if it had been a homework project. And so then she sent this 0% back to the AI system, and she got the following response. Thank you for the basically candid 0% homework verdict on my earlier attempt. It was precisely the clarity I needed. Well, I thought that tells you something about what AI understands at the moment. Anyway, I'm not going to talk any more about that. Let me go on to the next slide. This is the title, I should say. Classical and quantum realities are not quite the same. I'll come to describe what classical and quantum realities are, but the question I'm raising is, how about conscious reality? Now, I hope I can move my slides more onwards. Now, how do I do it here? I press a button somewhere. Oh, just the forward here. Okay.
Yeah, side to side.
I've used this slide before. It appears in my Emperor's New Mind book. It has to do with a Libet experiment a long time ago, the end of the the previous century. And I don't mean that end of the one before that, I guess. Yes, I'm getting a bit lost with centuries. But anyway, in this experiment, you could stimulate the skin, or you could look at the part of the brain had to be revealed. I guess it's an experiment which might not be legal these days, which is a shame because I think some version of it needs to be repeated. Anyway, stimulation of the skin. I won't go through the whole thing. I just want to mention one thing. If you go down 4 lines, it has to do with if you stimulate the skin and then stimulate part of the brain, which has to do with the stimulation of the skin. If you just stimulate the skin, there's a fast-moving clock, and the patient can say when that was felt, and it seems to have been felt almost simultaneously with the stimulation of the finger. But on the other hand, if you stimulate the brain first, and then about a quarter of a second later stimulate the finger, then somehow what would have been felt without the brain stimulation is sort of unfelt. And it's as though something happened in the timing. I'm only bringing this up, not because I want to talk about it particularly, because it seems to indicate there's something very peculiar about the timing of conscious experience. And in this experiment, you can see it almost as though something which should already have happened somehow can be wiped out as though it didn't have happened. And that seems like paradox. I won't go into this experiment anymore, but I just wanted to indicate that there is something very peculiar about the timing. Let's see, if I want to move forward, I'll press this button, I hope. Yes, these two gentlemen, I think I referred to in an earlier talk. The left-hand one is Einstein. It's really the one on the right that I'm more concerned with here. That's Kurt Gödel. And he had a wonderful theorem. And I want to refer to that theorem because it had a big influence. I went to lectures when I was a graduate student. I thought that 3 years was a long time, foolish me, and a long time, and I could go to other things which had anything to do with my subject, which was in pure mathematics. And I went to lectures by Bondi on general relativity, by the great Paul Dirac on quantum mechanics, both very important to me. And the third lecture was a course by Steen on mathematical logic. And this, he described eventually Gödel's theorem, and I want to describe the aspect of this which relates to consciousness. The thing is that you're presented with a set of axioms and so on, and what does Gödel say? It's a question of what is a proof made in mathematics. And you might say proof, you would say, is, okay, you've got these axioms and you've got these rules of procedure, and if you follow the axioms and the rules of procedure, that gives you a proof. So what does Gödel do? He constructs, this is a clever thing, of course, he constructs a statement which actually says, I am not provable by those rules. And it actually does that. That's the clever thing that Gödel managed to do. When you understand what the statement actually means, it means I am not provable by those rules. And then you say, okay, well, let's suppose it's false. Then it is provable by the rules, and it's provable by the rules, and it has to be true either way. So it has to be true and not provable by the rules. Now, how can something be true and not provable by the rules? Or more importantly, how can you see that it's true? Well, you can see it's true not by use of the rules, but by understanding why the rules work. And this was a real stunning revelation to me, because it says that conscious understanding goes beyond rules. It doesn't follow the axioms. It doesn't seem to follow the laws of physics as we understand them. Conscious understanding, after all, understanding in the meaning of the term implies that if an entity understands something, that implies that it's at least aware of it in normal usage of language. So it seems to say that awareness is involved in something which goes against computability. So I took this view from this lecture course, and I realized that it wasn't my subject, but still it seemed to me that it was an interesting fact that whatever consciousness was not the result of a computation. So that was the view I held. And let me try and move on to the next slide. Oh dear, something's going on here. Here we are, consciousness. I think that's all right. It relates to understanding. That is to say, I'm only talking about consciousness in this one particular aspect. Sometimes people complain about me. They say, well, I don't say anything about the perception of the color green or something like that. Of course, I don't. All I'm saying is one tiny aspect of consciousness, you might say, which is the element of understanding, the quality of what understanding means. And as I say, for an entity to understand something, the normal usage of language means that at least it must be aware. So there is something involved in awareness, genuinely in understanding. Let me move forward. This is, I should mention Cantor, who was very fundamental in the precursor of this idea. So let me move further. This is just a picture of sort of natural selection involved. And I'm trying to say that sometimes people say, oh, well, that's just mathematics and that's just a particular thing. But it seems to me it's very important. And the question is, how can somehow this quality of understanding have arisen by natural selection? Or being a mathematician, I try to argue, is not really valuable for natural selection, because I have in the background, I've got things which are valuable for natural selection, like people building shelters, domesticating animals, and in the foreground, building a shelter for catching this poor mammoth. And these are things which evidently would have helped people along and develop their quality of conscious understanding. And here is the poor mathematician in the foreground trying to prove a theorem. There's a little joke in that theorem, which I won't go into. I think it was the first theorem that was proved by a computer, I believe. And the idea was that this poor mathematician who just discovered this theorem, and this doesn't help him at all because he's about to be eaten by the saber-toothed tiger. The moral of this thing is that just being a mathematician and understanding subtle mathematics is not the point. That's quality of understanding, and understanding in general was what was selected for well, here also is a piece of mathematics, if you like. I'm just trying to indicate something which can be quite simple in a sense, but which is not computable. You can't put this on a computer. Now, what do I say can't be put on the computer? Well, the kind of problem here is the set of polyominoes. You see on the left-hand side, there are these four shapes made out of little squares, all equal squares stuck together, and they're simple shapes. And the question is, the general question is, if you're given a finite set of simple shapes, can you tile the plane with those shapes? And the answer is, there is no general algorithm for doing so. However, in any particular case, if you know that there is no general algorithm, then the reason you know this allows you to find a solution. In this case, there's a solution to tiling this problem. And it's a sort of challenge to see what the pattern is. It's very hard to see what the pattern is. There's no symmetry, there's no repetition, there's no thing of that sort. It's much more complicated. Why this will cover the plane. This is just an example of a non-computable problem. And so I got interested in these things because that seems to be a key to what consciousness can do. Okay, now here I sort of consider the various laws of physics, Newtonian mechanics, Maxwell's dynamics, Einstein's general relativity, Schrodinger's equation for the formulation of the evolution of quantum mechanics, the unitary evolution, and all these things you could put on a computer. So I'm looking for something that could not be put on a computer, at least we don't know how to, and maybe it could not be put on a computer. And the thing which is missing from all this is the collapse of the quantum wave function. So it seemed to me that the collapse of the quantum wave function, whatever it is, we don't have a proper theory of that, whatever it is something where probably, I would argue, is where the non-computability lies, and therefore that consciousness, whatever that is, would have to depend upon something of that nature. And here I'm giving the way we work with quantum mechanics. And in quantum mechanics, if you have a state A and another state B, then you can produce this linear combination alpha A plus beta times B, and that is a standard process in quantum mechanics, which means it's a sort of linear process. However, well, this here is a basic principle of general relativity, or which is the principle of equivalence, and it goes back to Galileo, and he described a big rock and a little rock falling from a leaning Tower of Pisa, and the fact that if you was a little insect sitting on one of the rocks, gravity is cancelled out. He gave another example, which is rather nice, where you imagine fireworks going up, And he noticed that as the fireworks drop, see, they make a beautiful sphere of sparks. And then as these sparks drop in the gravitational field, they remain a sphere. It's as though when you freely fall, you've cancelled out gravity. And in the bottom of this picture, I have a sort of futuristic 2001 type of space station, and the astronaut, even though the Earth is right there, doesn't feel the gravitational field because the astronaut is in free fall. So you can cancel out gravity with free fall. Now, how do you tie that in with quantum mechanics? And it's a bit of a challenge. And the thing we see is free fall equivalent to a force. See, there are two ways of doing a quantum experiment in which you want to consider the gravitational field. One way would just be to do the standard procedure, which any sensible physicist would use. You put a term in the Hamiltonian, whatever that means, but that certainly means a straightforward thing to do, and you just follow the rules. Now, if you notice there Galileo or Einstein sitting in the corner and say, oops, no, we should do it the other way, you just take a freely falling coordinate system, do the thing all over again. There's no gravitational field, and you do it all over again. And you find that the thing is almost exactly the same, except for this phase factor. That's this complicated thing. The wave function is this thing in green and psi, and the phase factor is this thing in brown, in black, I think, just preceding it with a colored thing in the exponent. And the thing in the exponent is the key thing, because it involves something involving the cube of the time. I won't go into all that, but all I'm saying that there's something very peculiar involving quantum mechanics and this basic principle of general relativity. There's been a recent paper, which I was slightly involved in, which is doing a nice experiment to show that this actual T cube term is physically present. It's not just a sort of mathematical trick. It's really there in the physics, and you can measure it. So let me move on, though, and to the next slide. And here, if you follow this through, this is the thing that many people didn't follow it through, but if you follow it through, you find that if you have a superposition of a body in two locations, you try to use that feature of quantum mechanics in a falling situation, then you find that you have to have an extra term in the energy, which has to do with the the gravitational self-energy of the system. If you have a body in superposition of two places, you can show there's a fundamental uncertainty in the energy of that system, and that energy can be estimated by imagining that if you had the body in two places on top of it, imagine two copies of the body, both on top of each other, and you pull them apart into this location where they're supposed to be in superposition, and you say, how much energy would that cost you to pull them apart when you only consider gravity? Very, very tiny gravity. All the other forces are far, far bigger. But if you just think of gravity, there's a tiny little force and a tiny little energy in pulling them apart, and the reciprocal of that energy gives you the lifetime of that superposition. So that's a nice way of describing the Dioschi lifetime, which I find later by the different method, and that's sometimes called the Dioschi-Penrose lifetime. He really did it first by some different procedure. However, there is something different about what he did and what I did, and there was an experiment recently to try, which seemed to disprove this lifetime. But I should say what it does disprove and what it doesn't disprove. You see, if you have a normal picture, a sort of ordinary quantum picture, and you try to make sense of this lifetime, then you think of in the body of a complicated body with all sorts of molecules in it, and you see if this jumping of the collapse of the wave function was happening all the time spontaneously, then it's like the body getting a little bit heated all the time spontaneously. And the experiment was done in the Gran Sasso experiment was to measure to see whether this heating took place. And they found it did not take place, which was my expectation. But in order for that to be an expectation, let me go into this subject a little bit more thoroughly. This is a space-time picture now, and I'm imagining that you have the body right at the bottom. That's the world line. As it goes up, that's time going up. That is the world line of the body. Now you're putting this body into two locations. So the dotted line means that it's now in a quantum superposition of two locations becoming separated, and then it collapses after this Dioschi timescale, and it becomes at point Q star rather than Q. And then the whole thing continues up at the right, at the left-hand side. Now, suppose you describe this picture according to an observer moving very fast in one direction or the other, but according to relativity theory, when one disappears and the other one appears, that's simultaneous only in one frame. If you have a moving frame, then sometimes the thing disappears before the other one becomes the whole state, or the other one, one of them disappears before the other one has become the whole state. And the other one doesn't make any sense, because it might mean there's also a probability of becoming two objects or none at all. And that certainly doesn't make any sense. So how do you make sense of this? Well, the only way I can see to make sense of it is a little bit more complicated than that, but the clearest way to make sense of it is to say that the reality goes right back to the creation point. So look at the diagram and look at the point Q, I think it's called. And the point Q, or is it O? I think maybe an O. You see that this is where the bifurcation takes place. And when the collapse happens, it actually as though it had already happened right at that point there. This seems to be crazy. I mean, how could it happen in a picture like this? When to make sense of this picture, what you have to do is to consider that there are two kinds of reality, classical reality and quantum reality. And that's in the title of the talk. What is classical reality? The classical reality is the sort of reality that we're familiar with, and it's sort of the reality of general relativity. See, when the body has gone one way or the other, it has a gravitational field, and the body is either there or in the other place. That's the classical reality. It's the kind of reality we're familiar with. But the classical reality seems to go back to the point where the bifurcation takes place. Quantum reality, see, classical reality has the form that you could ask the state, hello state, what is your state? And it can say, yeah, my state is such and such, that's fine. Quantum reality has a different kind of form. Quantum reality is when you still have the thing in the superposition in some sense, but you can't ask the system and say, what is your state? Yes, you can ask it that. It just looks blankly at you and says, I don't answer questions like that. Give me a yes or no question. I'll give you an example. A good example of quantum reality is the state of spin of a spin half particle. Now, the state of spin of a spin half particle I can describe by my right hand here. Its spin state has its axis of spin pointing where my thumb is. The spin is where my fingers are going, right-handed about the direction of my thumb. So any quantum state of a spin half particle can be described by a direction in space. So that is the quantum state. Now, suppose I try to ask the state, hello state, which way are you spinning? It looks at me blankly and says, I don't answer a question like that. But if I do answer, it says, give me a direction and try me. If I happen to get the right direction, say, are you spinning in that thumb direction? And if I've got it right, it'll say, yep, you've got it right, absolutely. I can repeat the experiment 100 times, 1,000 times. It gives you the same answer every time. This is a definition of Einstein. This is his definition of reality. This definition, there had been a sort of argument about whether the quantum state was real or not. And Einstein was saying, well, it has this kind of reality. It is real, he would say, because if you can ask a question, perform an experiment without disturbing the state, you can do that, you see. You know the direction it's spinning in, you can choose that, and you can say, are you spinning that way? And if with certainty it gives you the answer without changing the state, that gives it an element of reality. I'm saying that gives you an element of quantum reality. It doesn't give you an element of classical reality. Classical reality would be, okay, state, which way are you pointing? And it would have to say which way it's pointing. But you can't do that. That would be inconsistent with quantum mechanics. It's only quantum reality. It can only say, it can confirm. Quantum reality can be confirmed. It can't be ascertained. You can't say which way are you spinning when it's give you an answer to that. But you can say, look, I think I know which way you're spinning. It's that way. And it will say, yep, if you've got it right, 100%. Okay, so that's the idea. Finally, I wanted to give you a picture. Oh, it's disappeared on me. Here we are. There's a picture which is a nice example of quantum reality and classical reality. I want to make the point here. You see, the question is what's conscious reality? Well, we don't really know, but I think it involves the idea of quantum reality. It's something which somehow has got the timing very peculiar, and the timing is, in this picture, how peculiar it is rather indicated. And this is an example of what's called an EPR, Einstein-Podolsky-Rosen experiment, where we, in its Bohm's form of Einstein-Podolsky-Rosen experiment, time is going up the picture. Right at the bottom, we have the initial state. You have two astronauts, Alice and Bob, and they are each given a spin-half particle, which is initially in a spin zero state, split into two spin halves. Alice has one in a box that she doesn't look at. Bob has his in a box which he doesn't look at. And then they keep them in their boxes until they're way light years apart or something like that. And you can see their world lines have got separated. And then eventually Alice looks. She looks at her on the left-hand side. That's the topmost point on the left-hand branch. She looks at the state and tries to measure it in a particular direction. And it says, nope, you got it wrong. And that means it's in the opposite direction. That's fine. Bob doesn't even measure his until a little bit later. But the picture sort of indicates that this is what's so puzzling about the situation. If you try to describe the reality according to some very fast-moving observer, you can imagine moving very fast to the left, almost at the speed of light, or very fast to the right with the speed of light. And the only way to make a consistent picture is that when Alice has made her measurement, then Bob's measurement way back along the past light cone. You see that top left-hand point where Alice is making a measurement, and then there are diagonal lines going into that point. Those are the light cone of her past light cone, going right into the past and hitting Bob's half of his particle way before he's looked at it, even before, in a certain sense, before Alice has looked at hers, way along the past light cone. But it's become a quantum reality opposite to what Alice had found. And that sits there. Now, if Bob could say, hello, particle, what is your state? He could say it, but the particle wouldn't give him the answer. But if it would give him the answer, you'd have a blatant contradiction. Absolutely. The whole theory of relativity would collapse to the ground. It would be hopeless. However, it's only quantum reality. He can't ask the state. He can ask the state, but he just has to choose the direction of his own choosing. And then he can ask the state, what is your state? And if it's got it right, he's got it right, and so on. Think about this picture. I've mapped out all the different quantum realities all over the whole picture, and they're remarkably consistent. The quantum reality is completely consistent over the whole picture, even though it has a sort of retrocausal aspect to it. So I'm trying to say that quantum reality has a very peculiar relationship to time. It does not mean that you can retrocausal things. I mean, you can't go back in time and do things impossible, but you seem to be able to do things which are, I mean, I imagine that if you're a tennis player or something and you're trying to do something which would look like choosing something, a course of action, hitting the ball one down the line or cross court, and you're choosing that thing consciously, I would argue, even though people say, oh, it's much too late, all the muscle things, everything is all too late, there's no way that you could time it. But if it's quantum reality involved in the conscious choice that the tennis player has, then it can still be a conscious choice, even though it's sort of very, very peculiarly related to time. That's all I'm leaving you with. I haven't got an answer. I'm just saying with all these things that you try and bring together, which show you how peculiar quantum reality is in relation to our ideas, and it really needs to be understood. And this quantum reality is evidently part of what's involved in conscious reality. I think there's some kind of quantum and classical mixture of some kind, and that sure, there is something intentional which is involved in conscious decisions, but they can't be give you in a sort of quantum causal loop, which gives you a contradiction. And it very cleverly avoids contradiction but yet nevertheless it seems to behave in relation to the passage of time in a rather peculiar way. And that is the point I'm trying to make with this talk, that we have to understand much more about how quantum reality relates to the passage of time and how that might relate to the idea how conscious experience relates to the passage of time. Thank you very much.
Thank you, Sir Roger. That was awesome. We have some time for a couple of questions from the audience, so if we can get one of the mic runners to bring. Okay, I'm going to do it for now.
Thank you very much. Thank you very much. It is very much an honor, Sir Roger Penrose, for this opportunity to be able to ask you this question. I've been dying to ask you the question whether you are aware of the theorem, the free will theorem by Conway and Cauchy.
Yes, I've certainly heard about that. Yeah.
Yeah, so if
There's
so,
some new version I heard about, which somebody wrote to me about it recently. Yes.
Yes, and that
I think calling it free will is a little bit of a
yes, and that was probably the email probably came from myself. If you received it from a few weeks ago, possibly
yes,
that was me.
It may
myself.
well come from
yes,
you. Yes,
I'm glad that you are checking the emails, and I'm so happy to hear this.
That was the tetrahedra or something.
Yes, I just wanted to make a remark that it is interesting that you are trying to go in the forward direction, looking for the phenomena occurring in quantum mechanics to derive the consciousness of human, let's say, free will. This free will theorem by Conway-Cauchy is going the other direction. Let's assume that we humans have free will, that we can deduce that the quantum particles have free will as a consequence. And yes, I just wanted to ask, what are your thoughts?
Thank you very much for sending.
Thank you.
I hadn't worked on that for a long time. I remember I produced an example with a dodecahedron, which you could send, I think, two versions of it, one to here and one to a friend of yours, an Alpha Centauri or something. And seems to be that you send signals faster than light. But they're not as classical signals, they're quantum reality. So it's another example, I think, of the quantum reality issue. Yes. And the question, I think it's a little misleading calling it free will, but nevertheless, it is certainly illustrating a very peculiar feature of quantum entanglement. That's absolutely right. It's not something which obeys the normal rules of propagation less than the speed of light, if you like. You have these entanglement effects, which seem to be, they don't sort of go faster than light. They transcend it in a certain sense. It's like the Alice, it's a better example than the Alice and Bob ones, because you have a clear contradiction with a classical model. I think that's the picture, isn't it? I haven't thought about it for quite a long time, but they're very nice examples. Thank you very much for that example.
Yeah, thank you.
I think it was you, yes.
Thank you for that question. I saw Michael's hand go up next, and I read his paper on quantum consciousness, so I want to give him.
Thank you. Thank you, Dr. Penrose. Many scientists believe that the arrow of time is explained by the second law of thermodynamics and the increase in entropy of the universe. Do you agree with that, or might the collapse of the wave function be the actual source of the arrow of time?
Well, now on another topic altogether. You see, the arrow of time, you see, this gets me into cosmology. And I have a picture in cosmology, which is quite a different story from either things you're mentioning. The increase, it really has to do with a very different nature between the remote future and the Big Bang. And the point that I make is, though that's extremely different, when you look at it, it's only different in one respect. If you think of the geometry of space-time as sort of split into two things, one is the light cone structure. That just tells you that causality, every point, you can see which point can be reached by time-like or light curves. And this gives you the light cone picture. Now, the light cone picture of space-time is the conformal structure of space-time. And the conformal structure, if you look at the metric has 10 components, and the conformal structure, in other words, the light cone, is 9 out of 10. It's really the 9 independent ratios. So that you might say it's almost all the structure. The conformal structure of space-time is a very beautiful kind of geometry, and in some sense, it underlies the metric structure that Einstein's general relativity has. Now, the metric structure, you might say, is not much more. It's 10 components rather than the 9 independent ratios. Now, what is that 10th component? What is it measuring? Well, it's really the two most famous formulae of 20th century physics. What are they? Well, Einstein's E equals mc squared, which tells you that energy and mass are equivalent, and Max Planck's even earlier, a little earlier, E equals h nu or hf, tells you energy and frequency are equivalent. Therefore, frequency and mass are equivalent. You put the two together, and that tells you that frequency and mass are equivalent. In other words, any massive body is a clock. It ticks with a frequency given by its mass. That's what those two formulae tell you. So that tells you that mass is a clock. Now, what happens when you don't have that scale, when you don't have mass? When you don't have mass, you have a conformal picture. Now, when you have a conformal picture, well, the Big Bang, you might say, and the remote future, what could be more different? What I'm saying is, well, what could be more similar in a certain sense? Because the mass, that's a place, both places are places where mass essentially disappears. Mass disappears in the Big Bang because things are moving around so fast that when you look at the energy momentum vector of a particle, the mass of that particle is completely irrelevant. The geometry, the physics of what's going on in the very early Big Bang has nothing to do with mass. What about the very remote future? Well, for a quite different reason. You see that the particles which survive will be essentially Dirac particles. They satisfy the Dirac equation. You look at the Dirac equation and you see, well, the mass actually effectively fades out in the remote future. It becomes less and less important, and it becomes massless. The two ends become massless. So then you actually say that, well, the Big Bang and the remote future are pretty similar. You just have to lose your mass at a certain stage. And I've been promoting this model for many years. It's had received very recently some remarkable new evidence on the basis of some discovery by the young graduate student, when she was a graduate student, Alexia Lopez, and she's made a discovery which seems to support the model I'm putting forward. Very hard to fit it in with standard cosmology. So what I'm saying is that what determines the time scale is these remote future. The Big Bang and the remote future have this little difference, which has to do with the mass, and it's this little difference which affects the whole. Well, people say, what happens to the second law of thermodynamics? Well, you see, it goes into black holes. Now, the second law of thermodynamics is almost entirely the entropy in black holes. Black holes get bigger and bigger, they get bigger and bigger, and they sit there and sit there and sit there until the universe gets so low, so cold, that the black holes get even the biggest black holes become the hottest things around. By Hawking evaporation, they disappear. The black holes, according to Hawking, it doesn't matter really too much whether this is right or wrong, but I'm taking it to be correct. The Hawking evaporation takes place, and this affects, in the crossover between one neon and the next, it gets all squashed into a teensy-weensy little point, far smaller than the Planck scale, and all that entropy gets fizzled out in that little tiny point. So that's my answer to it. It's a very different answer, I'm afraid, from the ones that we've had there. But I think the difference is very subtle. about the time direction. It has to do with entropy increasing, but that's because the entropy was very low in the early universe, and the entropy goes up, and then it gets in these tiny little specks, and it gets bleeped out just at the crossover and becomes very low in the next eon. So that's my answer. Very different, I'm afraid. But thanks for the question.
You seem to be arguing that there isn't an arrow. In other words, there's no difference between the beginning and the end. Can you clarify that a little bit?
Well, there's no arrow in the laws. That's what I'm trying to say. You see, that I think the question might be that the collapse of the wave function contains a time arrow in it. I don't know. That doesn't feature in this argument. It's not the main effect. These are macroscopic gravitational effects, and the collapse of the wave function, that could be important in the story, it doesn't seem to feature very strongly. So even though there might be a time asymmetry in that, there is no obvious time asymmetry in that. The sort of time scales and things, you could work it the other way around. It's just that the states you start with are very low entropy compared with where they end up with. And that's what's going on all the time. And what starts off the entropy being very low is the fact that there's a sign change in the conformal picture. And it's just a tiny little sign change. When you look at the details of how the conformal geometry works, when you cross over from one side to the other, it looks pretty harmless. It's just a little sign change. But that little sign change gives you the difference between this hugely massive, concentrated initial state and this hugely remote, spread out final state. But conformally, they look just the same because the mass has disappeared. So it's a complicated story. But I'm saying that in this story, as far as I can see, it's not in the collapse of the wave function. Now, I'm quite prepared to believe that's wrong, and that it is somehow the collapse of the wave function is playing a role. But in this big story, the cosmological story, the collapse of the wave function doesn't seem to play much of a big role. That could easily be wrong, but that is my current thinking, I'm afraid.
Thank you.
Great, thanks. We'll take one more question. Let's make it quick because we're already out of time.
Okay.
Thank you, Sir Roger Penrose. This is Dr. Anita Goel. We've met before. You have often said that quantum mechanics is incomplete. In fact, you've even said it's wrong. And certainly Einstein and Schrödinger seem to share your perspective. And Schrödinger, in his book, What is Life, really tried to dig deep into this question in the context of life, living systems, and consciousness. And so my question to you is, what would this new physics, if our current theory of quantum mechanics is wrong or incomplete, what would the new theory of quantum mechanics include? Could it be that our current theory of quantum mechanics is a low-resolution theory, and it sort of averages over these conscious reality effects? And could it be that the new enhanced version of quantum mechanics plays those conscious reality effects in a way that has more experimental predictability? Almost like, like in one limit, it would reduce to the current quantum mechanics. Could you share your vision on how that roadmap could be built to the new physics and the new quantum mechanics?
Well, the argument is really, quantum gravity in reverse. You see, people often say, well, what the big unknown in physics is quantizing gravity. I'm trying to argue the opposite way around almost. You see, quantum gravity would maybe helpful, maybe to say something about what happens inside black holes, but that's not much helpful to physics of the world we're actually interested in. What happens inside black holes doesn't make much difference as far as I can see. But what is important to the physics of the world is the collapse of the wave function, which is happening all the time. And I am arguing that the collapse of the wave function is a gravitization of, it's the other way around, if you like. It's not the quantization of gravity that's important, it's the gravitization of quantum mechanics that's important. It's when gravity, the effects of gravity come into the quantum formalism, that's when you see the collapse being a genuine effect. It's not just some observer looking at the system or something like that. It's genuine physical effect, which unfortunately no experiment to date has been subtle enough to see this effect. There is an experiment which is in process, in just being set up by my colleague Yvette Fuentes, and I'm hoping that she will get some answer to this while I'm still alive. I don't know. It's certainly a challenge. Even that is only looking at a sort of side effect to the collapse of the wave function. It's not actually directly seeing the collapse. But the argument would be that the collapse of the wave function is a genuine physical effect. It's not the observer or something like that. It happens when the bodies get too big. And the lifetime is, in fact, that one, which I call the Diyoshi lifetime. I found it independently, but he found it about 2 years earlier than I did. We're using a different argument and not quite the same theory. But I'm claiming that that lifetime is probably a good measure of how long a quantum state can exist. And if you're looking at atoms, molecules, then they can last for a long time, maybe longer than the age from the Big Bang to now. However, if you're looking for a grain of sand, no, that'll go in absolutely no time at once. It's the Diyoshi lifetime for a grain of sand in two different positions would be instantaneous. So would be nice to see other experiments which are groping for trying to see this effect. It's very difficult to see in an experiment because you have to keep all the environmental decoherence out of the window, and that's the problem. You have to keep your system in this quantum state of superposition for long enough that the environment doesn't get involved, but long enough to see the predicted quantum effect taking place, quantum reduction effect taking place.
Great, thank you.
I know that fits in with the cosmology. It's not altogether clear to me. It seems to be a different story. They must fit together, obviously, but I don't see how the stories do fit together as yet.
Thanks very much.
Somebody would tell me that I'd like to see it.
Maybe there are some budding physicists in the audience today that could come up with such an experiment to help Roger out there. Okay, sorry, that's all we've got time for with this session. I know we could talk to Roger all day long, but we will give him one more round of applause to thank you. Thanks so much.
Thank you very much.
Excellent. Well, thanks, everyone. Okay, our next speaker is William Brown. William Brown is a biophysicist investigating the physics operational at the cellular and molecular level of the biological systems. He's a part of the research team at the International Space Federation, a research and development company generating novel technologies in geometrodynamic and quantum vacuum engineering, harnessing energy from the zero-point field. William has applied discoveries from his biophysics research to technologies that can be utilized for great health and system coherence. Please welcome William.
Thank you. Thank you all for coming, and I hope you will enjoy my presentation today. I work with the International Space Federation, and actually my background is in cellular and molecular biology. In fact, some of my postgraduate work research was in investigating neuronal cytoarchitectonics, because what I was looking at is how the architecture of the brain can be involved in consciousness. And actually, during the course of that research, one of the things that became apparent is that the brain has a fractal architecture, a fractal structure. So actually, what I needed to look at in addition to the macro scale neuronal architecture was actually subcellular cytoarchitectonics, in addition to the larger geometric structures of the brain. Now, at the subcellular level, when you're talking about cellular cytoarchitectonics, you're at the microdomain. These are macromolecular assemblies. So this is involving quantum physics. So I actually needed to begin investigating the biophysics of the microdomain of the subcellular system of neurons and other cells associated with the brain. Now, I had the great privilege of getting to team up with the brilliant physicist Nassim Haramein and his group of physicists, his research group. And what I've been doing since that postgraduate work is looking at how to develop a unified physics model of understanding consciousness and brain function. And I'm going to present some of that model today, and what is termed instantaneous memory accession via quantum geometrodynamic circuits. And one of the reasons I think that this is valuable to this conference and the science of consciousness is that this model is not only an extension of the Hameroff-Penrose orchestrated objective reduction model, and not that it's going to be, or that I'm going to be discussing the generation of consciousness per se. That's covered by ORCO-R and the DOZ-Penrose objective reduction mechanism, but actually looking more at a specific aspect associated with cognition and more generally sentience, and that is memory. So with this extension of the ORCO-R model, I believe we can describe a non-computational mechanism of memory, and that non-computational aspect is actually, I believe, also a validation or verification of Penrose's original postulate that consciousness involves non-computability, and actually I believe we have a mechanism, a physical mechanism that demonstrates that. So first, do we need to go beyond what we already have, the conventional understanding of neuronal brain function? That is, roughly speaking, it's encapsulated by the neurocomputational paradigm, in which the brain function is a result of neurocomputational functionalism. I'm going to look at why this model is erroneous. One of the things, and so the neurocomputational model obviously treats the brain like a computer, and that's kind of just where we're at with science, is that you know, computers are kind of our pinnacle of technological achievement, and there's kind of this proclivity to equate every physical mechanism with a computation. It's a computational process, and there's some benefit to that, but I'm going to show why it falls short when you're talking about the brain. And one thing that we can look at on why it's erroneous is when you're talking about what Hameroff has termed the cartoon model of the neuron. And that's why I've heard him say neuroscience needs a revolution. And with the cartoon model of the neuron, it's kind of, roughly speaking, that the neuron has synapses, and the synapses are logic gates. They function as an on-off state. But this already is erroneous because the neuron is not a simple logic gate. It's not a simple on-off state. Actually, it's a complex multi-unit processing system. And so we can take the neurocomputational functionalism, in which the synapse represents a bit, and we can look at, does that account for observed phenomenon? Is this model in agreement with reality? One of the things we can look at is a condition called hyperthymesia. So you've all heard of amnesia. Amnesia is when you have a total loss of memories. There's a converse condition to that called hyperthymesia. And that is a condition where instead of losing all memories, you can never lose a memory. So individuals with hyperthymesia, they have extensive recall of events of their lives. Within the neurocomputational paradigm, this kind of condition is not well described, to say the least. And in fact, it was not believed that this would even have been possible. So actually, it wasn't even described until as late as 2006 in a comprehensive, rigorous, empirical method. And that's because these individuals have extensive recall of almost every day of their lives, and it's almost automatic. The way they describe it is you give them a date, and that day is almost automatically recalled, and they see it play as if it's a movie playing in their mind. Now, this has been quantitatively assessed, and it is definitely statistically significant, the anomalous type memory that these individuals with hyperthymesia have. Now, note that they're recalling it almost as if they're watching a movie play. So we can equate this, if we're saying that that memory is a computational process and is being stored as bits, we can do a calculation. Okay, what does the neurocomputational model suggest is the memory encoding capacity of the brain? Because that is what is going to have to account for this anomalous, extraordinary autobiographical recall. And what we can do a pretty simple calculation. It's rough, but it gives us an estimate. We know quantitatively, kind of precisely from actual cell counts, about how many neurons there are in the human brain. And again, so this is rough because this is talking about neurons, but there's also supporting cells like glia and that kind of thing. But we know approximately how many synapses some of these neurons have, and we can give an approximate number. And so it's really straightforward. We just multiply these together, and we get the memory encoding capacity of the brain, which is about 1 petabyte, a quadrillion bytes. Now, 1 petabyte can store approximately 15 days of continuous uncompressed 4K video. Now, for most of us, that's not a problem, because 15 days ago, I don't recall what was occurring in my life with vivid clarity, as if a video's playing in my brain. So obviously, I forgot some of it. Actually, I probably forgot a lot of it. So that's why, under normal conditions, the neurocomputational paradigm can kind of skate by. It makes it through unquestioned. But with hyperthymesia, we have a situation because some of these individuals, let's say they're with hyperthymesia, let's say they're around 60 years old, that amount of 4K video storage would require about 1,000 petabytes, a 1,000-fold increase over 1 petabyte. That's an exabyte. So the neurocomputational paradigm, or conventional model for explaining memory in the brain, is inadequate. And you know, the situation is a little bit more complex. I've just given kind of an example of how it falls short. And actually, I was very generous on the amount of memory capacity I gave to the brain under computational functionalism, because actually, if you talk to a neuroscientist, and I did yesterday after our workshop, you know, they explained, well, actually, you know, we think that the conventional understanding is that memory is occurring in the hypothalamus. So my calculation was this entire structure, but if we look at the neuronal cytoarchitectonics, actually the structure of the brain that's involved in memory is this little guy here, the hypothalamus, which is about 0.5% of the total brain volume. So my petabyte approximation is wrong. Again, roughly speaking, if we look at, okay, well, so memory's here, that's 0.5% of total brain volume, and we have a quadrillion bytes here. Actually, the memory encoding capacity is 5 terabytes. That's the size of an external hard drive. I have a 5 terabyte external hard drive here with me. So that can store a good amount of data, a good amount of information, but definitely not an entire lifetime worth of extraordinary autobiographical recall. And then, you know, so it's also that, you know, you have the understanding that in the computational functionalism, the synapse is a bit, but you also have things like synaptic potentiation. But really, that's just the kind of synaptic plasticity that's occurring and forming new memories and getting rid of old ones. So synaptic change, the like long-term potentiation that you see associated with memory is definitely associated with memory. Might be more of a indexing or tagging mechanism, but not necessarily storing memory. And so what I'm going to explain here is how memory self is perhaps read out from a multiply connected space-time topology with some of these subcellular structures forming a registry or a tag of that memory trace. And this would make long-term potentiation, synaptic weights, or Hebbian plasticity associated with memory be more like access keys or coupling parameters in a larger space-time information network. It's not the synapse. There's good reason to believe that the cartoon model of the neuron doesn't cut it. It doesn't explain observed, documented, quantified phenomenon like hyperthymesia. Let's look at how we can perhaps go beyond that. And one way, pioneered by Hameroff and his colleagues, is by going to the subcellular level. So we have synaptomic architectonics. And let's look at the structures that are in the synapse. The synapse is obviously involved with the correlates of consciousness, the correlates of memory, forming memory traces. And even in the postsynaptic density here, you can see this macromolecular assembly. Normally, under the conventional model, this is just scaffolding. So what we could posit here is that this postsynaptic density is not just scaffolding. It's a dynamic structure, and being a macromolecular structure comprised of molecules, it's involving quantum states and quantum phenomenology. And we see that, so we've got things like our actin network that is directly connected to microtubules. The ability for synapses to form requires microtubule entry into the synapse, so that for neuronal plasticity, you need microtubule activity. So there's no question microtubules are involved in brain states and consciousness in that way, and the correlates of consciousness. We've got our macromolecular assemblies in the subcellular microdomains, and these, as depicted here by Hameroff, these macromolecular assemblies necessarily involve quantum states because they are quantum systems, quantum level objects. We can begin to look at what kind of quantum states could be involved in that subcellular cytoarchitectonics in developing a memory trace. And one of the things is that we are looking at a quantum gravitational mechanism just like orchestrated objective reduction, and so we're looking at how that could happen via a unified physics model of the biology involved. Now normally, so that involves space-time structure just like the orchestrated objective reduction event that has the bifurcation of the space-time structure to lead to collapse of the wave function. Now normally, the space-time at our normal scale of existence and what we can measure, we know that it has geometry, right? That's something that comes from general relativity that's pretty largely understood. I might ask a geometry of what, because space-time's often, just described as a vacuum, and it's almost, the geometry is thought of as like an abstract thing. I'm going to show it's not, because actually what is typically thought of as like a smooth, continuous geometry, if you go down to small scales, high energy scales, this is at 10 to the negative 35 meters, the Planck scale, it's actually a multiply connected topology, a multiply connected geometry. So it's not simply connected, it's not a smooth, continuous topology. And actually what Nassim and our work and our research team's work has shown is that by looking at the pixelation structure of quantum space-time, you can actually look at how, like with correlation functions, the coherence dynamics of this quantized space-time structure, and you can explain how it forms space matter, or little particles, hadrons, what we're made out of. Space matter particles. So this is actually work from our Nassim and our ISF research group. And what you have is, so we have the quantum vacuum. So the electromagnetic energy density of the quantum vacuum at the Planck scale here is actually so large that it curves space-time. And this is work that was done by Wheeler, and it's more commonly known as quantum space-time foam. But actually what happens is it curves space-time so greatly that it begins to encapsulate space-time. Space-time becomes infinitely curved. And what we have here is the formation of little space-time voxels. So this is a discretized structure of space-time at the quantum scale. And discretized structure, space-time voxels, can encode information. So this led us to the idea to posit a term we call space memory, that information can be encoded actually in this quantized structure of space-time. And when you apply the understanding of, what we call these Planck spherical units or space-time voxels, when you apply it to the understanding, looking at them in very coherent phases, you can actually describe the hadronic scale. You can describe particles like the proton. And one of the things we have here is an Einstein-Rosen bridge that forms from this quantized structure of the proton. That Einstein-Rosen bridge is actually more commonly known as a wormhole connection. And what we have from this work is the understanding that all protons are connected together in a multiply connected space-time topology. Every proton is connected to every other proton via that fine-scale structure of space-time, which is always there, the quantum space-time foam. Now when we're talking about how long do coherent states to quantum states last in the brain, that's an important consideration, but one of the things is that the matter that we're made out of is always connected at the Planck scale via this nonlinear connectivity circuits, what I call geometrodynamic circuits. So even if a quantum state might have come and gone, let's say in the subcellular domain, it's the protons that macromolecular structure in the brain is made out of is still connected via its space-time architecture, multiply connected space-time architecture. And actually with the solution, you can see like the number of space-time voxels on the surface of the universe. If you take the observable radius, the radius of the observable universe, and you calculate how many space-time voxels, those little geons, that's a gravitationally bound electromagnetic object. Those are the PSU encapsulations. If you count how many of them are on the surface of the sphere formed by the radius of the observable universe, it's actually equivalent to the same number of space-time voxels that cover the sphere of a volume that's at the radius of the proton. So the number of space-time voxels on the surface of every proton in the universe equals the number of voxels on the surface of the universe. That's a holographic ratio, a holographic principle. When we're talking about those subcellular cytoarchitectonic domains, these structures that are involved in forming the quantum states, like the chromophore residues, the tubulin and the microtubules, the aromatic rings, amino acid ring structures, these are made out of protons. And as we've shown, those protons have a multiply connected space-time topology via, they're connected together via Einstein-Rosen bridges, and they're connected to the quantum scale of space-time structure as well. And that includes many different kind of macromolecular assemblies. So the same is true of DNA. So in future work, we might explain why DNA is a memory molecule. We believe this could have a lot to do with that. The structures that we're talking about in the tubulin are made out of protons. This is a depiction of a proton which is connected to every other proton and also the quantized structure of spacetime. A note on what these spacetime geometries are that I'm talking about. I touched on this a little bit on the workshop yesterday, but I'll just reiterate here so that it's clear for anybody who might have missed the talk yesterday, is that you have, as far back as 1935, Einstein and his colleague Rosen attempting to solve the particle problem of physics in general relativity, because what has now become the standard model describes particles as point-like objects. And this leads to a whole host of problems, particularly in general relativity, because you have pathological spacetimes like singularities. Their solution was to extend particles, extend their description as a spacetime geometry, and that's where you get the idea of wormholes. Einstein, or as the more technically known, Einstein-Rosen bridges. Now, wormholes, as they're popularly known today, we usually think of these as like cosmological objects, large astronomical objects out in space. The way that they were originally discovered was in describing particles. Actually, today, a popular idea is that we can describe particle behavior, and particularly quantum states like entanglement, via an underlying space-time topology. So that's a unified physics description of particle behavior, particle states. We could describe entanglement via the underlying space-time geometry. And actually, one of the first, the description of this entanglement phenomenon also came from Einstein and Rosen and their colleague Podolsky. So this quantum state is called EPR pairs. And importantly, especially when we're talking about macromolecular assemblies in the cell, these entanglement states aren't just between two particles. Even recently, there's been work that has described multi-system entanglement of large assemblies of molecules like what you would have in the microtubule. So this is where we get to the extension of the Hameroff-Penrose model. So we're no longer talking about the quantum state of superposition, but instead the quantum state of entanglement, and the fusion of these two ideas, that the Einstein-Rosen bridge topology is equivalent to Einstein-Podolsky-Rosen correlation. This was first posited by Leonard Susskind and Juan Maldacena in the conjecture ER equals EPR. So within the tubulin, where you have these chromophore residues interacting, they're forming entanglement structures, and that entanglement structure is entangled with the fine-scale structure of space-time. So what happens is that as you're moving along, you're imprinting memory traces into the structure of space-time, and you're non-locally connected with that imprint into the space-time structure. Because remember that the quantum space-time foam is always there. It doesn't require some kind of special mechanism to keep that non-local connectivity circuits of space-time. It's always there. And also an important consideration, so this is a space-time diagram. We have a space-time, and this is a world line. We're going along this world line. An important thing to remember is that you're always moving. So even when you think that you're sitting still, like in this room, you're actually moving quite quickly with quite a high velocity through space. You're on spaceship Earth which is orbiting the sun, and the sun is moving through the galactic plane. So there's no shortage of information surface on the fine-scale structure of space to imprint information on. Space is very large, which is why if you're talking about like hyperthymesia, and the information is being imprinted into the structure of space and then retrieved via the potentiation traces of the synapse, there's no limit to how much information can be encoded and retrieved quasi-instantaneously through the non-local connectivity circuits of space-time geometry. This is one of the neurons in your brain going along this world line, and it's having molecular scale interactions, which are involving quantum physics, and part of the description of those interactions involves those molecules forming entanglement states. That entanglement state is actually entangled all the way to the fine-scale structure of space-time, and it's leaving a memory imprint. That's what these wavy lines emanating from the microtubule is meant to indicate. And then as you go along, you have different kind of configuration states, different kind of, let's say, topological qubit states on the microtubule that are being formed, and that's imprinting. But when you need, let's say this is a memory formation event. When you need a memory recall event, you can go through that non-local connection, that entanglement structure, and recall the quantum state of the microtubule, and the memory is reformed. Now, just a quick note on the physics of that memory imprint into space. So you're always moving through space. Sometimes you're aware of you're moving through space, sometimes you're not. And, but the matter of which you're comprised is always vibrating the space-time structure. And so it's always leaving an imprint in the space-time structure. And actually, we can see the significance of this in some of the more recent work of Nassim Haramein and the research team, in that they've shown that high energy density of the quantum electromagnetic vacuum that in high coherence phases is forming the particle, the proton, they've shown that via a mechanism called the Zeldovich effect, it's actually converting to gravitational waves. This is involved in forming the mass and some of the confinement forces of the proton. But every molecule is emitting gravitational waves. So you're vibrating the space-time at a fine scale all the time, and you're connected to that all the time via this non-local connectivity circuits, geometrodynamic circuits. If you're vibrating the structure of space-time, these are not evanescent structures, not evanescent modes. Via things like gravitational memory effect, they're leaving permanent imprints in space-time structure. And what's important to note about this is that gravitational memory effect, it involves not only changes in position, but also momentum. So actually what you're talking about is a frequency. When that information is being transmitted via something like the gravitational memory effect, it's a frequency. And we know a lot about how that can be involved in information transmission from electromagnetic transmissions, which all the information is encoded not digitally, but actually in the frequency modulation and amplitude modulation of the signal. So again, that's a non-computational information transmission mechanism. And so we're talking about an oscillator. So the way that this memory trace is affecting the quantum state of the tubulin is via affecting those dipole oscillators, the chromophore residues. And so, you know, our proton that's emitting gravitational waves is a carbon nucleus here, so we're already in the biological domain. But so your neuron here that is emitting gravitational waves, which is being recorded in the space-time structure via gravitational memory effect. And as you go along your world line, you're imprinting this memory into the geometry of space-time itself, the fine-scale quantized structure of space-time geometry itself. So let's say you had a memory formation event here, that is imprinted, the memory trace is in the fine-scale structure of space-time. Now, let's say you want to recall that event, you're entangled with it, the information can come through, excite the quantum state, and you have something like super radiance, described and documented by Philip Currian, and that's going to affect the synapse activity. That's been documented by Annabelle Bandiopadhyay. Here you can actually see those references. And I think there was a question even yesterday by the neuroscientists, do microtubules affect neuronal function? It absolutely does. It's been observed and documented. So like brain oscillations are generated by microtubules. So if you're getting the right quantum state to your microtubule, you get the right quantum state to all your microtubules, you recreate the same neuronal state, you recreate the same brain wave pattern, that's the memory. That's the conscious correlate of that memory. Okay, so that is the gist of the idea.
Actually, one question. Thank you. Thanks, William. That was awesome. We've probably got time just for one quick question for William. So, yeah. I don't want to pick the front row again. Sorry. Yeah, I'll go back here.
Thank you very much. I remember reading that in Nassim Haramein's work that the proton actually, when it cycles, with each cycle, it updates all the other protons and all their information. So what you're telling us, is this also accounting for the holographic principle?
Yeah, exactly, absolutely, yeah. So Nassim and his group has actually calculated the refresh rate of every proton in the universe. And the way that physically occurs, because that sounds like a pretty phenomenal thing, that every proton is informed from every other proton. How could that possibly happen, especially when general relativity says that there's a speed of light limit on how fast you can transmit a signal? Well, general relativity also says that there's a shortcut to that speed of light limit, which is the Einstein-Rosen bridge, quasi-instantaneous information transmission. That network, that neuromorphic network of space matter nodes that are the protons, are able to exchange quasi-instantaneous signals so that the entire universe is updated at about 10 to the negative 23 seconds. And so it is a unified whole, but that's definitely a holographic principle that you have at play there. But so, again, just to stress, you're made out of that quantized space-time structure. You're made out of those protons. So you're forming these entanglement structures with the whole universe. And you can see that in other quantum physics formalisms. I mean, like Bohmian mechanics has a universal wave function. The Wheeler-Feynman interpretation of quantum mechanics has a universal wave function. So these things are actually part of the some of the canonical descriptions of quantum physics even.
Thank you, William. Let's give him another round of applause. Our final speaker of the day will be James Tagg. James is an inventor and serial entrepreneur who trained in physics and computer science at Manchester University and engineering at Cambridge. He's most famous for inventing the projected capacitive touchscreen, which is found in all smartphones. He also founded the Penrose Institute, which studies the interface between quantum mechanics and general relativity and its implications for human consciousness. So let's welcome James.
Hi. Hi there. Right. Are quantum computers already conscious? Let's get controversial. Okay, so what do we mean by consciousness? Well, David Chalmers is very famous for one of the early versions of this conference, getting up on stage with a hairdryer that he'd hijacked from his room and pretending it was a consciousness meter and going, well, you're conscious and you're not, and offending half the front row in the audience. But I'm going to use the definition which I quite like from broadly speaking, Roger, which is a functional definition, that consciousness allows us to do something that non-conscious machines can't do, namely solve non-computable problems. And my experience of consciousness is because I live in one of those devices. I must not use the word machine. Why is this super interesting right at the moment? Well, we're watching LLMs gather a pace, and some people are estimating that they will be smarter than us in 2 years' time. So we will become as pets. So the same effect that dogs have with us, we will then become the pets of AIs, which I would hope is not the case. So we do know that computers have certain limitations. Those limitations are theoretical, from Gödel and Turing. So Alan Turing kind of invented the computer in his paper, and that's the one about computable numbers, which is unpronounceable according to the movie. And so computation back in his time was people in rooms writing out longhand mathematics. And he said, well, look, you could make a machine, you could conceive of a machine that could make any one of those mathematical calculations. And then you could say, well, does that machine solve every problem, right? Can it tell me whether I marry Mary or any arbitrary human problem? And he did this really clever little kind of computing trick or mathematical trick where, there's statements like, this statement is a lie, which are inherently contradictory. So he came up with a computer program and said, well, if there's a machine that will solve every possible problem, I can feed it itself. And he came up with this machine that basically you say, will I not crash if I feed it to myself? And he showed that generates a paradox, and so that machine can't exist, and therefore computer programs can't solve every problem. Meanwhile, in mathematics camp, there was a chap called David Hilbert, and he said, well, mathematics is complete. There are these two books. There's the original Newton book, and then there's the other Principia Mathematics. And if we get to like volume 11 or 12, we'll have done mathematics. It's completely consistent internally, doesn't require any external validation. And then Gödel came along in his doctoral thesis and said, no, that's wrong. Mathematics is incomplete. Mathematics is basically just puzzles, right? You just move, you have some axioms, some rules, they're matchsticks, you can do these things with the matchsticks, and then you can move the matchsticks, and then you can prove something, right? Slightly more complicated than that, but not much. So you have axioms and rules of inference. And what Gödel said, and I mean, I've misunderstood this. I went and read all of the presentations I've given for the last 10 or 15 years of this conference. I've never really understood this problem until very recently. So why can't you just make a machine that discovers all mathematics, right? Why can't you just tell it to run? Why on earth can't you do it? Because every theorem you could ever think of, you can just write down, right? It's just symbols. So you can enumerate every theorem. Why can't you just give that to a machine and say, go until you find me the problem, the answer? And the reason fundamentally is that there's an infinite number of mathematical theorems, right? You could add axioms. There's an infinite number of axioms you could add that make perfect sense mathematically, but are just wrong. And an infinite number the other way around. So the problem is you can't say to the machine, go find me a new axiom that makes sense, because it'll come up with an infinite number that make sense but are just wrong with respect to the universe we live in, and an infinite number that are right. And you do not have infinite time to look at it, so you can't solve it. That's the fundamental problem that Gödel gives you. And just to give you an example, right? What do you mean by right and wrong? Here's an example, nice example with a sting in the tail, which is geometry, right? Euclidean plane. We live in a flat universe, but it's perfectly possible to create geometry with curved universes in it, right? Perfectly rational. You won't get a syntax error from your computer, but they don't make any sense because that's not the universe we live in. And that's the case for all mathematics. You can come up with an infinite number of mathematical theorems that are perfectly consistent, pass syntax error in any kind of theorem prover, and yet make no sense. Now, of course, the laugh here, of course, is that when you get to Einstein, we do actually live in a curved universe, or potentially curved universe, but on massive scale. So then you have to think, well, you have to understand scale. Well, computers don't understand scale. They just understand what we tell them. So that's the fundamental problem. Now, there's a theorem by Harvey Friedman. So he says, yes, okay, computers are theoretically limited. This is known, right? But you don't care, right? You will never find a theorem proven in the Annals of Mathematica, which is the equivalent, you know, I don't know if whatever field you have it's the top dog, it's nature or whatever. You'll never find something that isn't provable in a tiny subset of even Peano arithmetic, just simply proven. And the problem with that is that, well, he might be right, but I think he's wrong. I think you do find problems that are solvable, and whether he's right or wrong, if you can add an axiom and short-circuit your proof so that you take something that's intractably, you know, complex and you can do it very quickly, then that's a really useful feature to have. So I think he's wrong in both ways. He's wrong, you do find mathematics that is more complicated, and he's wrong in that, okay, he might be right, but if I can find a clever axiom, I can outperform a machine. Non-computable proofs, it's a field that's been moving quite rapidly. And of course, now with LLMs, you can just ask them, say, right, give me a list of all the current non-computable proofs that are out there that's been proven by mathematicians that required extended axioms. And it gives you a whole bunch. So it's now a field that you can actually do research on, whereas, you know, 3 or 4 years trying to find a proof would take you months of tedious effort. So this is what LLMs give you, research. So an Awk-OR machine does something really cool. It allows us to build, I must call it a machine, right? Roger will kill me, right? Machines and computers have a meaning in mathematics, right? They're what, you know, can machines think? That's what Turing defined a computer to be. So I must always use the word device. So a thinking device. It's not a computer and it's not a machine. Let's go build one. So the first thing I did, I got stuck in COVID, and I couldn't. I actually had my O visa had run out, so I couldn't work for anybody. I hadn't got my green card yet. I hadn't got my work permit. But you can do theoretical physics research in your garage without breaking immigration law, as I understand it. And so I did this. I was supposed to go into the UCSD, but I phoned them up and I said, you know, I'm ready to come in. Thank you very much for the space you offered us, Will and I. And they said, there's 2 problems. One, you're not faculty, and we're not only letting faculty on site because of COVID. 2, it's Will and James. We're only letting 1 researcher in each lab. So you fail on 2 counts, you can't come in. So we built it in the lab. And so this is a clever little experiment. This is not what I'm going to talk to you about, but I'm just going to quickly tell you what it is and why we sort of put it to one side. So we built this experiment to try and prove just objective reduction. So it's a single bit gravitized quantum computer, just 1 bit. And what it does is very simply takes a photon, puts it through a half-silvered mirror, has that detected by 2 single photon avalanche diodes. Those 2 single mode avalanche diodes move 2 mirrors, right? So you've got 2 mirrors that moved. Did one mirror move or the other mirror move? Remember, it's a single photon. So at the end of the day, only one mirror can move because you've got 1 photon, because there's got to be a measurement. And the question is, where's the measurement? And does it take time? And the answer is, I've given this presentation a few times before at this conference. And yes, it does take time. Yes, you can see it. But I could spend another 2 or 3 years of my life in the garage, fiddling with this machine, trying to get to the point where nature will accept it and publish it. And my wife said, just stop, right? Assume it works. Assume it works, right? Because do you really care? You don't have a PhD. You're not a practicing physicist in a university. Do you care? What you care about is, can you make the machine? So I said, well, okay, I should make one. And she said, well, what are you going to build? I said, well, I could go biological or I could go hardware. She said, well, pick one or we'll do both. So we picked one and did the other one as well. So the first thing to do is we're making a biological computer. What we do is we take a skin sample from you, convert that to a stem cell, then grow an organoid from it, then for why do you do it? Because human brains can do single-shot learning without needing a nuclear reactor, so it'd be a very useful piece of equipment. And then we bring them and we make an array, 32 by 32 array. That's 1,000 of these small miniature brains made out of human tissue, which is a 1/16th model of the human cortex. And then we just treat it like a D-Wave machine. We say, we think you're a quantum computer, and we're going to write to you and read from you as if you are and see if you are. So it's like an adiabatic quantum computer. Solution number one. Huge advantage, it's massively scaled, right? It's got billions of gate equivalents, right? The largest quantum computer today is probably about 1,000 bits. This has got 1 billion bits, if it works, right? So this is project number one. We do send them to space, the organoids, as they go up to the International Space Station for 30 days, and they come back down. And the reason is that brain tissue, biological tissue, matures around 10 to 100 times faster in space. In fact, a brain organoid will get to 10 years cognitively and 80 years biologically in the 30-day trip to the International Space Station. And it's like the Jesuits, like, give me a boy until 7 and I will give you a man. So it's terrifically useful to have an organoid that's 10 years old rather than 3 months old, because it'll lay down permanent memories and all sorts of fun things like that. So then we took a look at the IBM computer, and this is actually the title of my presentation. The wonderful thing so the problem with my garage experiment is it's at room temperature, it's extremely difficult to do, it's very, very noisy. We do get a kind of positive result. As I said, I could spend at least another 3 years on the stats. The nice thing about an IBM quantum computer, it's got billions of dollars of research into. It's an extremely well calibrated machine. It pulls hard vacuum. It goes down to, millikelvin, right? So it's already a $1 billion experiment. And you get 10 minutes a month for free if you give them an email address. I have 8 email addresses, so that's quite a lot of computing time. I did go and actually see the head of them and tell him I was doing it, and he said, that's fine, James, well done. What does an IBM quantum computer look like? It's a heavy hex model, so it's got lots of, let me just go back. You see all those little circuits? Each of those circuits is a qubit. They're arranged in this sort of hex pattern, so they're near a few neighbors so they can work, and they are wired up with these gold-plated copper tubes, which are microwave, microwave waveguides, that fire microwaves in, flip them, and then use the same technique to read out. So that's what's in them. So the problem is I need some gravity, because it's a quantum gravity theory, not a quantum theory. Where do I get the gravity? Well, the only place I can think of getting the gravity, let's just go back, these bits are tiny, super tiny, thin film transistors. Stuart, I, and Roger went to the Google quantum computing, and they had kindly calculated how long it would take it to spontaneously collapse. And I think it was either 10 to the 7 or 10 to the 9 years. It was like forever. Right? So these things won't collapse. They're designed not to collapse. That's why they're cold, vacuum, everything. The only place I can find some gravity, potentially, is in this copper wiring. Right? It's kind of got to have enough gravity to collapse the wave function, because it's the way you measure them. And when you measure them, you get a classical result. So at some point in the process, I get a classical result, and these are maybe the culprit. What am I looking for? Well, I have Schrödinger's cat, so the chip is in a superposition of 1 and 0, and it's going to collapse. It's going to pick one choice or the other due to gravity. And I'm going to look for it. But there's a problem, right? Which is, there is no statistical difference between this, let's see if I can do this correctly, and put it in my pocket, and a day later take it out carefully and put it down, say, is it heads or tails, or for me to flip the coin in real time. Those will both look identical. So how on earth do I sort of tell that it's like the tree falls over the forest, right? Does a tree fall over in the forest if you don't look at it? Well, the only way to find out that the tree fell over in the forest when you weren't looking at it is to go to the forest and see, right? So how do you separate observation from spontaneous gravitational collapse? It's mind-blowingly difficult to work it out. But there is a trick, and the trick is that you can split your quantum particle in two. Now, you can't do this with a photon, obviously, or most things. Actually, you can do it with a photon. It's difficult to do, but it's quite easy to do in an IBM quantum computer because they are superconducting qubits and they're made out of lots of electrons. So you can actually split them, and it's a fairly routine thing to do. The problem then, experimentally with this, is that Stewart and Rogers' theory has this E sub g term. So I need a mass and a time. Well, IBM doesn't give me any parameters for their microwave system, right? And if you phone them up and ask them, they can't give it to you either. It's like, we don't know how heavy it is in a Penrose sense. We don't know. But the nice thing about the IBM Qiskit system is you can do a lot of tests. So you can just say, I don't know, so I'm going to be exhaustive. I'm going to try every possible mass and every possible time. So, 250,000 experiments later, you've tested everything that's testable. So it's either possible to solve or not. So we went all the way from, there's crosstalk in an IBM chip. If you measure the bit on the top left-hand corner, it will affect the top right-hand corner. That's the least coupled that you can be. We went all the way from basically measuring the bottom right-hand corner to see if that had an effect on the top left, to entangling every single bit on the chip and taking a mass measurement with every single bit. So let me just sort of give you the trick as to how we did it. So we're going to do a little bit of quantum mechanics. So you get some weird things in quantum mechanics. First thing is you can have a 100% alive cat, put it through a Hadamard gate, it'll go 50-50, put it through another Hadamard gate, and it'll be 100% alive again, right? Sounds pretty weird. What's a Hadamard gate, just in case? Actually, this bottle of water is a pretty good Hadamard gate. So every photon that comes through, let's say, a glass, some of the photon is reflected and some of the photon is transmitted. So that's effectively a Hadamard gate. If I had a compact mirror here and I was able to get the photon that had bounced back to recombine with the photon that went through in another glass, this sounds like a bit of Hitchhiker's Guide, but then I can actually do this experiment even in the bar. I don't have any measuring equipment, so I can't prove it, but I've done the experiment. So it's actually relatively simple to do this, and this is the bread and butter of what an IBM computer does. It lets you do these sorts of experiments. And if I do it to a particle, no one worries at all, right? That's completely normal quantum mechanics. Then you have this issue that if you open the box in the middle, the cat is now definitely alive or definitely dead. If you've taken a definitely alive cat and a definitely dead cat and you put it through a Hadamard gate, it's 50-50. It's 50% one way, 50% the other way. Again, with cats, it makes no sense. With particles, we do this all the time. This is just what we do. We look at the experiment and we see. So what we decided to do is to peek. We're going to take a partial measurement. We're going to have a little look in the box rather than a full look in the box. And then there's a difference between what the Penrose theory and what sort of standard quantum mechanics would say. So in standard quantum mechanics, I look at something and the thing I look at collapses, right? The observer collapses it. That's what happens. But in Penrose, what happens is when I put something into superposition, space-time curves in two different ways, right? So it's the whole of space-time is curved. And if I actually take a peek at something with sufficient gravity, it will collapse space-time. And what that means is using gravity to collapse is the equivalent of doing a full measurement. So if I do a gravitational measurement, I will collapse everything. If I do a quantum mechanical measurement, I will get half collapse. So this is the circuit we built. It's the standard Qiskit circuit. Get a bit, do a partial measurement, and then what we trickily do is we do basically a branch. So an IBM computer will let you branch on the result of a quantum measurement in circuit. So you take a result and you do a branch. Now the branch then fires the microwave array, because the microwave array has now got to reset 2 bits. And what we do is say, if you made a 0 measurement, set bit 1. If you made a 1 measurement, set bit 2. Right? So we're actually causing the machine to move differential mass depending on what it did. So we're using that to force the computer to have mass attached to a gate. So we've got now a high mass. So if Penrose and Hameroff are right, the result that you get should be 50-50, near 50-50, because measurement in the Penrose model gives complete collapse of space-time. And if they're wrong, it should just be 75-25, which is the standard one. And the answer is they're right, that it does collapse the wave function based on the mass that you apply to it. So I will get around to open source. Oh, the nice thing, of course, is the big problem with my garage experiment, it would have taken 5 years for someone to then replicate the experiment. With this, any kid can go into Qiskit with 10 minutes free time on the thing and run the experiment. So I will open source the GitHub soon, and you can all just go and have a go and tell me if I got it right or wrong. I'm sure I'll get lots of, you missed this or missed that. I am doing quite a lot of control experiments to pick out all the different sort of things that might throw you off, but you get a pretty consistent, tendency to this 50-50. If you put a lot of mass, it goes straight 50-50, right? So it's also mass dependent. So it's closer than the 50-50 to control. Penrose and Hameroff are right. Gives some interesting consequences. One of the interesting consequences, effectively, what you've got is a 3-phase situation in this system. You've got the purely quantum phase, where you set up a quantum circuit and it's all happily quantum. And then you make a measurement in the circuit. Now, that measurement is not yet a measurement. It's called an improper mixture. So you have decohered it by making the measurement, but you haven't actually collapsed it. And then when you go and do the final measurement and you actually give it some real mass, that causes a collapse to classical. Interestingly, you can do useful computation in the improper mixture state. Now, you cannot do Shor's algorithm, all bets are off, because that requires perfect entanglement and so on, but you can do Grover's. Grover's is basically unstructured search. Unstructured search is, I have a phone book, I'm looking for your name, someone annoyingly has randomized all the names in the phone book. How many entries do I need to look at to have a 100% chance to find your name? The answer is every one, because your name might be the last one in the phone book. With a quantum computer, then you get root n. If you look at root n of the number of entries in the phone book, you have a 100% chance of finding the person's name. In a quantum gravity Grover's, you can do it in a single operation. Right? Single operation will find something in unstructured search. Now, unfortunately, it's incredibly noisy, and if unstructured search could really be done that well, then we'd have all sorts of weird things going on. It'd be like monsters from the id, and we'd be able to do anything, with our brains, which we can't do. But even a slight modification to statistics makes things that are vanishingly unlikely or impossible possible. And one of the things which I've been discussing a little bit with Stuart is the origin of life. So you could have replication-induced objective reduction, where the replicating element causes mass to increase. It is decohered because it's a mess in there, right? All biological systems are a mess, but it's an improper mixture. So an improper mixture can still do certain elements of quantum computing, in my theory anyway. And so I think that opens up a whole realm of things that you can do with these machines. That's how the brain gets around this problem that it can't do non-computation. It uses some sort of non-computing algorithm of this sort of nature to basically change the odds from vanishing likely or 0 to very unlikely but not 0. And that's my talk.
Thanks, James. I have time for some quick questions for James. I'm going to go to a different part of the room this time. Anyone right at the back? Let's go right to the back. Any questions over here? No? Okay.
Go on,
you already had a question.
Yeah, her question will be a good question. It's a plant.
Thank you, James. That was very nice. So just to follow up on what Roger said earlier, can you do this modeling with the interplay where quantum reality, classical reality, and conscious reality are all part of the mix?
Oh, gosh. I think the answer has to be no. I haven't fully absorbed the consciousness to classical reality yet. I mean, you do have the benefit that in quantum reality, time is not yet ticked. So you can do all sorts of things where you're allowed to go back in time because time doesn't exist yet. So you're not really breaking any laws. And we know from David Deutsch that one of the things you can do is you can have closed time-like curves, which can then exceed a Turing machine. So there is some wriggle room in the laws of physics there where you could get a theoretical way by which you can actually exceed a Turing machine. And I mean, that's what I'm arguing here that you're doing. You're exceeding it. But I'll need to spend a bunch of time on Roger's classical quantum. I spent a little bit of time, but not enough.
Any more questions for James? Yep.
Yes, Suzanne. Thank you, James. It was spectacular. You just lost me at the last slide. Can you go on as well? So basically, okay, quantum, okay, classical, in the bit, the interesting part.
The improper mixture.
Yeah, that's the part where I would like you to dig a bit.
Well, if you have a fully quantum state and it decoheres, what does it decohere to, right? So normally your state would have some density matrix. And it will decohere and it will basically zero out the off diagonal, right? But it's not chosen which thing it will do. So are there any useful computations or useful things you can do with a state that hasn't chosen what it's doing yet, but has lost all forms of coherence? And the answer is, in a pure quantum computer, no. Once it's lost coherence, it's useless. But in a quantum gravity computer, yes, because you can run quantum gravity Grovers. And so you can do unstructured search in an improper mixture. And so what I think is potentially happening in the brain is you can do unstructured search in improper mixture, which is the sort of roundabout way of answering Anita's question, which is you're doing something that would give you a way out of the laws of physics as we know them at the moment. That's the trick.
Hello. I have a question. Yeah? I have a question.
Oh, yeah.
Sorry. So according to your report, and we can see that you support the idea that the quantum consciousness in human brain, right? Quantum consciousness. You support the idea?
Yeah. Do I support quantum consciousness? No. I support quantum gravity consciousness.
Okay.
Yes.
So, can you give some comments about some researchers? They said that this quantum FS, maybe quantum entanglement happened in the machine's brain. How do you think about that?
In which machine's brain? Ours or?
Quantum entanglement,
yes.
Quantum collapse happens in the machine's brain. They said that there's a quantum consciousness in AI's brain. How do you think about that?
If I understand the question, yeah. So, I mean, quantum computers collapse all the time, right? Yeah. That's what they do when they fall apart. And an IBM quantum computer collapses in about 300 microseconds.
Yeah. So do you think that the quantum orbit or quantum entanglement and quantum collapse happened in the AI's brain?
In the
AI, the machine's
in the
brain.
AI?
Yeah, machine's brain. Do you think that happened?
I don't think it's useful. I think it did collapse, but that's not useful. What you need is this complex sort of gravitational entanglement to give you something that will then give you computational power. We are looking for something that's more powerful than Turing machine.
Okay, so there's no quantum consciousness in the machine's brain?
Can you make an, well, it's a proto-consciousness idea, right? Which is, in order for you to have consciousness, you're going to have a complicated machine, big enough to have thoughts. You're going to have programmed it. It's going to have lived some time, so it has some memory, so it can apply this capability. It's going to have a lot of stuff. So at the moment, unfortunately, I'm toying with the very base layer, which is there something that you can see that the machine does that is not just a Turing machine? Because if it's just a quantum computer or just a classical computer, it's just a Turing machine, and it can't do non-computability. So I defined my conscious definition at the beginning, which is it needs to be more powerful than a Turing machine. Where could it get that power from?
Okay, thank you for the answer. Thank you.
Just one more question over here.
Perhaps you've just addressed this, James, but yes, I'd like to take you back to your first point where you said consciousness, something that can solve non-computable problems. And you very nicely explained how that can apply to the brain. Are you saying that that can or will apply to quantum computers?
You could make a device. We would not call it a computer anymore because we want to respect Roger's view, but we would call it a device. You could make a piece of hardware that could do non-computable mathematics, and therefore, if that's our definition of consciousness, that's our theory, and that is the Penrose theory, then yes, you could make a device out of silicon or germanium or some photonic thing, whatever, that would be conscious. And we are just, you know, biologically conscious machines with this, I used machine again, we're biologically conscious things that do something that's more powerful and more interesting than just a computational machine.
And then perhaps we'd have to look at some of the other things that we do and experience that might not be then in that device that is able to do non-computational calculations.
Well, I think I wrote in my book, plug book, that I think, for example, humor is a mating display. It's it's non-computable, and if you look at, you know, it's survival of the most adaptable. So you notice that people tend to marry the more creative people, not necessarily the most wealthy. They're looking for someone who is adaptable in a non-computable way. So I think telling a joke is the way that you explain to someone that you're non-computable and you're adaptable and, you know, you're worth marrying. And so it's like it's a mating display. Now, so therefore, if, you know, the next version of ChatGPT comes out and gets on Saturday Night Live, I'm toast, right? There's a counterexample.
Okay, thank you. I think we can go further, even with the ideas of subjective experience, phenomenology, and the experience particularly of qualia. And I think those will have to be seen to how they emerge from that model of quantum consciousness. Thank you.
Thanks. Oh. Did you want to comment on that, James?
I mean, I don't understand qualia, and I don't understand. I understand, like, someone tells a joke and someone laughs because I can measure the degree of laughter, how many people in the room laughed, and I can then get a machine and I can say, right, tell a joke, ChatGPT, and everyone goes, oh, gosh, like a dad joke. I can measure it in some objective way. Qualia, I don't know how I measure it. It's like, my sensation of the color blue is much better than yours. No? Oh, you're just fantasizing. You know, it's just an argument with, you know, it's a pub argument, as we call them in England. You can't, it's not science.
Very quickly.
Just a clarification. It's not a question. This is not a question, but a clarification. We need to make a distinction between a decision process that is being non-computable versus being able to solve non-computable problems. I think in the questions there was some fuzziness in the, but I just wanted to mention this.
Yes, we can spend many hours on those arguments. I'm trying to just stay at a high-ish level. Yeah.
Okay, thanks everyone. Let's give James another round of applause. Thanks, James. So that's the end of this session. Now we're going to have a quick break, and we're also going to reconvene for concurrent sessions at 5 p.m. So they will be going on in a variety of different rooms. That will run till 7. And then after that, we have the poster session. So please join us for the rest of the day's activities. Thank you.